In this section, we'll dive into IPset. Let's see first why do we need IPset. IP tables itself does not support matching multiple separate addresses or networks in one rule. If you want to block 10 different networks, you have to create 10 different IP tables rules. This means that every checked address or network would need their own rule in the rule set. Such complicated and long rule sets bring administration and performance concerns. Just imagine what would happen if you want to block 100,000 networks or IP addresses, or why not an entire country. You have to write 100,000 IP tables rules. Even though you can simplify the configuration by using a bash script that reads the IPs from a file, the performance degradation would be of a real concern. Each packet would traverse all 100,000 rules from top to bottom and would be checked by each rule. I can honestly tell you that I've seen a CPU overhead between 10 and 30% only for IP tables. This is where IPset comes into play. IPset is an extension to IP tables that allow us to create firewall rules that match entire sets of addresses at once. Unlike normal IP tables chains, which are stored and traversed linearly, IPsets are stored in indexed data structures, making lookups very efficient, even when dealing with large sets. It lets you create huge lists of IP addresses and ports with tens of thousands of entries, which are stored in a tiny piece of RAM with extreme efficiency. In your IP tables rules, you can then simply refer to the lists by name, and the entire list is checked with remarkable speed and in a single IP tables rule. These IPsets are a framework inside the Linux kernel and can be administered by the IPset utility. On many Linux distributions, you have to install IPset, which is a very simple operation. If you are using a Debian or Ubuntu-based distribution, you just run apt install IPset. Let's go to a terminal and install IPset. First, I'll try to execute the IPset command to check if it's already installed or not. Don't forget to run all these commands as root. Use sudo before the command name or become root by running sudo su or su. It depends on your distribution and your configuration. I've just run the IPset command and we notice that IPset is not installed, and it also tells us how to install it. So I'm typing apt update and then apt install IPset. If you are using an older version of Ubuntu, use apt-get instead of apt. And if you are running CentOS, execute yum install IPset. Now IPset is installed. Let's check the installation by running IPset help pipeless. Okay, in this lecture, we've seen what is IPset, when do we use IPset, what advantages it brings, and how do we install it. In a nutshell, IPset brings significant performance gain and powerful extra features, like the ability to apply single firewall rules to entire groups of hosts and networks at once. Anytime you want to apply firewall rules to groups of hosts or addresses at once, you should be using IPset. In the next lecture, we'll dive deeper into IPset and see many more examples. In this lecture, we'll see the first examples with IPset. IPset is a mesh extension for IP tables. To use it, you create and populate uniquely named sets using the IPset command line tool and then reference those sets in the mesh specification of one or more IP tables rules. Let's consider the following normal IP tables rules that block incoming packets from these three source IP addresses. Alternatively, the following IPset and IP tables commands achieve the same result. The first step is to create a named set. Remember that a set is simply a list of addresses stored efficiently for extremely fast lookup. IPset -n, let's say my set, #IP. I am creating a new set called mySet. -n means create a set. And it's an uppercase letter N. #IP is the method of storing and searching the collection. I'll go into more details in the next lecture. The second step is to add the IP or the network addresses to the new set. So IPset -a from add, it's an uppercase A, the name of the set, my set, and the IP address. The first IP address, the second IP address, and the third, the last IP address. And lastly, we reference the set in a mesh specification of IP tables. Before writing the IP tables rule, I just want to test that I can communicate with 8.8.8.8. This is the public DNS server of Google. Perfect, it's working. And now the IP tables rule. IP tables -a input, the chain, -m set, --- set, the name of the set, my set, src from source, -j drop. The IP tables command references the set with the specified name, and it means match packets whose source IP address matches or is contained within the set named mySet. The flag src means match on source. There is also the flag dst, which matches on destination. Let's test the connection to 8.8.8.8 again. And ping doesn't work anymore. Let's list the firewall. And we notice there are 6 packets dropped by the rule. Also note that only one IP tables command is required regardless of how many IP addresses are contained within the set. This example uses only 2 IP addresses, but we would just as easily define 10,000 addresses and it would still require only a single IP tables rule. Without IPset, so using the traditional IP tables approach, the setup would require 10,000 IP tables rules. In the next lecture, we'll dive deeper into IPset and we'll see how to use it in depth. Let's move on and dive deeper into IPset. Let's see how to create sets. When working with IP tables and IPset, the first step is to create the named set. It will contain the IP or network addresses. In the last lecture, we've seen that if we want to create a new set, we use -n. Let's try a new example. IPset -n, the name of the set, let's say China, it's a random name, you can choose whatever name you'd like, #net. It's also possible to use the create option instead of -n. IP set, create, Romania, the name of my country, #net. Now if the set already exists, you'll get an error. Sometimes you want to run a script that creates some sets and does other stuff without worrying about the case when the set does already exist. And I'm running the command again. Set cannot be created. Set with the same name already exists. To avoid the error of an existing set with the same name, use the exist option. If exist option is specified, IPset ignores the error otherwise raised when the same set already exists. And if the set already contains some IP or net addresses, they are not flashed. So I am adding -exist. And there is no error. Each set is of a specific type. The type defines what kind of values can be stored in it, IP addresses, networks, ports, and so on. The most common type sets are #net and #IP. #net is the same with nethash. Nethash or #net is used for a collection of networks. And #IP or IP hash, it's the same, is used for a collection of individual IPs. The difference is how efficient the storage of the collection will be and how fast the kernel will search in the collection for matching packets. Besides these two types, IP hash and nethash, additional set types are available to check the port, the IP address and port together, or the MAC and IP address together. Let's move on and see other examples with IPset. If we want to add a given entry to a set, we use the add option. IPset, add, the name of the set, China, and the network, 1.0.0.0/8. Instead of add, you can also use -a, an uppercase A letter. It's the same. If you try to add an entry that already exists in the set, you'll get an error. Element cannot be added to set, it's already added. If the exist option is specified, IPset ignores the entry if it's already added to the set. -exist. And there is no error. Let's list the sets and their entries. We've created some sets with some entries. IPset list or IPset -l brings out all sets with all their contents. We see the name of the set, some parameters, and the entries. Now if you have many sets and want to see only one set, you add the set name, IPset -l China. And it printed out information only about China set. To delete an entry from a set or a collection name, use del or -d option. IPset del China 1.0.0.0/8. Okay, sorry, there is an error. It's an extra dot there. This command has deleted the entry from the set. I can also use -d instead of del. So -d. It's the same. To flush all entries from a set, use flush or -f option. IP set -f China. It flushes all entries from China set. If I write only IP set -f without specifying the set name, it flushes all entries from all sets. -f or flush. It's the same. To delete or destroy a set, use destroy or -x option. IP set destroy China. It has removed the set called China. The set with the given name does not exist. I can also write IP set -x Romania 1. And if I write IP set destroy without specifying the set name or IP set -x, it deletes all the sets. Take a look at this error. Set cannot be destroyed. It is used by a kernel component. Note that a set cannot be destroyed while there is a single reference pointing to it. So if there is an IP tables rule that uses the set, you should first delete that IP tables rule and only then destroy or delete the set. IP tables -VNL. And we see there is a rule that references my set. So IP tables -f, I'm flushing all the chains and tables. Now there is no rule in the IP tables firewall. And I can simply delete the set or all the sets. So IP set -x will not raise an error. And there is no set. Maybe you wonder how many entries can a single set contain. There is a parameter called maxLM which defines the maximum number of elements which can be stored in a set. By default is 65,535. This parameter is valid for the create command of all hash type sets. Let's create a new set that can store a maximum number of 5096 elements. IP set create my set #IP, the set type, and now max lm 4096. Sorry, I've forgotten the parameter. So max lm and the number. Perfect. IP set list. And we see information about my set, and max lm is 5096. In this lecture, I'll show you how to automatically block bad hosts. IPset provides a target extension to IP tables that provides a mechanism for dynamically adding and removing set entries based on any IP tables rule. Instead of adding entries manually with the IPset command, you can have IP tables add them for you on the fly. For example, if a remote host tries to connect to port 80, but there is no HTTP or web server running on that machine, you could consider it bad and block it entirely. It's like a proactive measure to avoid something nasty it could do in the future. Let's see how it works. First, I'm destroying all the sets. And I'm creating a new set called auto-blocked of type IP hash. IP set -n auto underline blocked, the name of the set, X type IP hash, and also -exist. I don't want an error if the set already exists. The second step is to add an IP tables rule that adds IP addresses to the set based on some criteria. So IP tables -i input -ptcp -d port 80. So if the packet comes to port 80, -j set -add -set the name of the set auto-blocked and src. I am adding the source of the packet to the set. If a single packet arrives on port 80, its source IP address is instantly added to auto-blocked set. It's like you'd manually run IP set -a auto-blocked and the IP address, the source IP address, like this. It's the same. Only that IP tables does this automatically for us and does it on the fly. And the third, the last step, is to reference the set in an IP tables rule that drops the packets. So IP tables -i input -m set -match set auto-blocked src -j drop. Perfect. Now I'll ping continuously from my Windows recording machine. Let's see the IP address of the Linux machine, and I'll ping it continuously. Okay, to ping it continuously, you use -t option. And it's working. Now from a second terminal, I'll send a packet to port 80. And I'm gonna use the telnet command. Telnet, the IP address of the Linux machine, and the port 80. At this moment, ping is still working. Okay? And enter. We see how ping stopped. It stopped because it automatically added the IP address, the source IP address, to that set and dropped all the packets. Perfect. Let's check it. First, let's check the set. I have created a new set without adding an IP address. So IP set -l and the name of the set. And we see the IP address of the Windows machine in the set. Let's list the firewall. IP tables -vnl. And this is the rule. It has dropped 19 packets. This is a very nice and useful feature of IP set and IP tables. You can use it in your network. In this lecture, I'll show you how to clear the running firewall. If you want to completely flush IP set and IP tables rules and reset to an open firewall state, you should set the accept policy, flush all netfilter tables, delete all IP tables user-defined chains, flush all IP set entries, and destroy all sets. This is useful to use at the beginning of any firewall script in order to flush everything and built it from ground up. And I'm creating a script called stopfirewall.sh. Okay, the first step is to set the policy to accept. iptables minus pinput accept, and the same for output and forward chains. Next, I'll flash all tables. iptables minus t filter minus f. I'm flashing the filter table. iptables minus t ra minus f. I'm flashing net and mangle. Next, I'll delete all user-defined chains if there is any. iptables minus x. Okay, we are done with iptables. Now ipset minus f. I'm flashing all the sets. Then ipset minus x. I am destroying all the sets. And that's all. I am saving the script. Set the execution permission. And run the firewall. Perfect. iptables and ipsets have been cleared. Keep in mind that sets that are in use and that means referenced by any iptables rule cannot be destroyed. First flash the iptables chains and then destroy the sets. Now you should have a good understanding of ipset and iptables in order to build customized firewalls. In this lecture, I want to show you something really cool and useful. Suppose we run a Linux server with many services like HTTP, FTP, SSH, mail, and many more. Over time, we notice in server's log a lot of authentication attempts, scans, or other kind of malicious traffic. And we want to build a file with all the source IP addresses that tried to attack our server and completely block those addresses. This is the perfect scenario for ipset. For this example, I'll create a new file called badhosts.txt. And I'll write some random IP addresses in the file. And I'm saving the file. Perfect. Now I'm gonna create a bash script that reads the IP addresses from that file, creates a new set, adds the IPs to the set, and then references the set in an iptables rule that drops the traffic. For example, band.sh. The first line indicates that this script will be executed by bash by default. I'll store the name of the file that contains the IP addresses in a variable. This way, I can rename the file or use another file easily without modifying the entire script. File equals, and between double quotes, the name of the file. bad_hosts.txt. This is a relative path. badhosts.txt and the script called band.sh are in the same directory. Feel free to use an absolute path if you want. I am creating a new set called badhosts of type IP hash. ipset minus n badhosts IP hash and minus exist. Further, I'll add the bad addresses to the set and do all other required stuff. Finally, I'll run the script. Running the script more than once means that it will add each IP address to the set more than once. To avoid this issue, at the beginning of the script, I flash the set. This means that each time the script is run, the set is flashed and then all the IP addresses are added to the empty set. So here I am flashing the set IP set minus F bed hosts. Good. I don't like scripts that are not verbose. I want to see messages to know what the script is doing. So I'm printing a message. Adding IPs from file to bed hosts. Now comes a very important part. Using a for loop, I'll read each IP address from the file and add it to the set. So for IP in a pair of backticks and a comment cat $file, the name of the variable. Do and done. These are backticks or back quotes. This is the key just below escape on your keyboard. A backtick is not a quotation sign and it has a very special meaning. Everything you type between backticks is evaluated or executed by the shell and the output of that execution is used there. It's just as if you'd type that output at that place in the command line. In this case, it's like we copy and paste all the IP addresses in that place. So here. In fact, I am iterating over a list with IP addresses. And inside the for loop, I'm adding the IP addresses to the bed hosts set and I'm also printing out the IP. IP set minus A bed hosts $IP, the temporary variable of the for loop. And echo minus n $IP. I'm using -n option because I don't want a \n or a new file after each IP address. All IP addresses will be printed out on a single line. -n prevents echo to add a new line after printing the string. Outside the for loop, I'm printing out another message. Echo -e -n and between double quotes \n, this means a new line, and dropping with IP tables. -e enables interpretation of \escapes like \n, which is a new line. And finally, the last step is to create the IP tables rule that actually drops the packets. IP tables -i input -m set -match set, the name of the set bed hosts. I'm matching on source IP address, so src -j drop. And echo done. Okay, I have noticed a very small problem. If I try to flash the set before creating it, I'll get an error. You cannot flash a set that doesn't exist. So I am moving the command that flashes the set after the set is created. Perfect. The script is done. I'm saving the script. I'm adding the execution permission and I'm running it. Okay, no such file or directory. The name of the file is bed_host.txt. And inside my script, the name of the file is bed hosts, so there is an extra s at the end. No problem, I'm renaming the file. I'm running the script again. Perfect. It printed out adding IPs from file to bed hosts set, the IP addresses, and the message from IP tables. IP set -L bed hosts. Perfect. The IP addresses are in the set, and IP tables -VNL, and we see the rule that references the set. That's good. Let's check it. Ping 8.8.8.8 and ping doesn't work. Now I'll remove that IP address from the file. I'm simply erasing that line, saving the file and running the script again. Perfect. That IP address is not in my list anymore, and I'm trying the ping command. And it's working. Now you can simply add or remove IP addresses from the set by simply adding or removing them from the file. This is a very useful firewall script for any sysadmin, and I can say that I have such a script on each Linux I administer. In the next lecture, I'll show you something really cool. How to drop entire countries using IPset and IP tables. See you in a second. Hello and welcome back. In this lecture, I'll show you something really cool. This is one of my favorite use cases of IPset and IP tables. Suppose you have a business localized in a specific country or region and you don't have any business relations with some parts of the world. Like say you have an online store that sells shoes and delivers them only in Europe. It would be a great security improvement to drop all traffic originated from America or Asia. You are selling only in Europe. The classical way to do this is to use a service that provides a collection of networks from a specific country. Then, using IP tables, you create a rule for each network address that drops the traffic that's coming from that network. Even though it's working fine, the performance degradation is of concern. You have to add thousands or tens of thousands of IP tables rules, and each packet will traverse from top to bottom and will be checked by each rule. The best practice in this case is to use IPset. It lets you create huge lists of networks with tens of thousands of entries which are stored in a tiny piece of RAM with extreme efficiency. Then you can simply refer to the set by name and the entire list is checked with remarkable speed and in a single IP tables rule. In this example, I'll block all the traffic that originates from China. It's just a random country, you can choose any country you'd like. Okay, let's start creating the script. In fact, this is just a variant of the example from the previous lecture where we've banned all IP addresses saved in a file. I'll skip some of the explanations because I've already done it in the last lecture. I am creating a script called blockchina.sh. At the beginning of the script, I'll print out a message. I want to know what the script is doing. And a new line. We start by creating a new set of network addresses. IPset -n China #net x type -exist. This creates a new hash set of network addresses named China. Then I'm flashing the set. We've discussed why this is necessary in the previous lecture. IPset -f China. This bash script will download a file that contains all network addresses from China. Each time we run the script, we check if the file exists, and if it already exists, we remove it and download a brand new file. So I am checking if the file already exists. The name of the file will be cn-aggregated.zone. If the file exists, I remove it. And I'm downloading the file that contains all the networks from China using wget from ipdeny.com. There are many services available out there, but I've used this successfully, and it's also an updated one. I am searching for China, copy the URL and paste it in my script. I'm choosing the aggregated zone file because I want to drop entire networks, not individual IPs. It's more efficient this way. wget and I'll paste the URL. In Linux, each command has a return status, which is 0 if there was no error and not 0 if there was an error. We can get the error status of the last executed command using the question mark predefined variable. I'm checking the return status of the last executed command, and if it was successfully executed, I'm printing out download finished. And another new line. The next step is to add the networks to IPset. Now, using a for loop like in the previous example, the one from the last lecture, I add each network from the file to the China set. This file contains all networks from China. For net in cut and the name of the file between backticks or back quotes, IPset -a China $net, the temporary variable of the for loop. And I'm printing out done. And finally, the last step is to create the IP tables rule that actually drops the packets. The rule will reference the set called China. IP tables -i input -m set -match set, the name of the set src, I'm matching on source IP address -j drop, and echo done. I'm saving the file and set the execution mode. Before running the script, I want to check that I can visit a website hosted in China. And I have this example. It's working great. I'll execute the script. Now it's adding networks to IP set. Perfect. We see how it downloaded a file called cn-aggregated.zone. This is the file that contains the networks from China. After the script has finished executing, I check the site again. And we notice that the site is not loading anymore. All packets that are coming from China are dropped. Let's list the IP tables rules. And we see 200 dropped packets by the rule that references the set called China. Now if you want to see the contents of the set, you simply run ipset -l China. If you already have a firewall script, you just have to execute this script from your main firewall script and it will add this configuration to your existing one. Okay, that's it. Thank you. Hello and welcome back. In this section, we'll dive deeper into IP tables targets. A target is the action that is triggered when a packet meets the matching criteria of a rule. There are two types of targets: terminating targets and non-terminating targets. Terminating targets perform an action which terminates the evaluation within the chain. The packet matched by the rule will not continue traversing the current chain or any other ones in the same table. Depending on the target, the packet might be dropped or accepted. Drop is such a terminating target. For example, if the matching criteria of a rule drop the packet is dropped and no other rule will be evaluated. On the other hand, a non-terminating target performs an action and then the evaluation within the chain continues. The packet continues traversing the rules in the chain. Each chain must eventually pass back a final termination decision, but any number of non-terminating targets can be executed before that. Log is such a non-terminating target. For example, if the matching criteria of a rule log a packet, the packet is logged and then the next rule within the chain will evaluate the packet. Let me show you a first example of a terminating target. In a new shell script, I'll write two IP tables rules. The first rule will accept incoming SSH traffic and the second will drop any TCP traffic. Both accept and drop are terminating targets. I'm writing the rule that accepts SSH traffic. IP tables -a input -p TCP -d port 22 -j accept. And the rule that drops all other kind of TCP traffic. IP tables -a input -p TCP -j drop. Let's think for a minute what will happen. When an SSH packet arrives, the Linux kernel will accept it and the packet will not be evaluated against the second rule. That's because accept is a terminating target. The second rule will evaluate only TCP packets other than SSH and drop those packets. It doesn't matter if there are other rules that are accepting the packets. Drop is a terminating target, the packet is dropped and will not continue traversing the chain. Let's test it. I'm saving the script, then make it executable and run it. Let's try to connect to Linux 1 using SSH from Linux 2. and we notice that SSH is working. That's because the first rule has accepted the packets and the second one hasn't evaluated them anymore. If I list the firewall, I will see matched packets by the first rule. There are 12 matched packets, and no packet matched by the second rule. Notice that the second rule hasn't matched any packets. Now let's try to connect to Linux One using a browser. There's a web server running on Linux One. In the address bar, I'll write the IP address of Linux One. And the page is not loading. If I list the firewall again, I'll see that the packets are dropped by the second rule. There are 8 dropped packets. Let's move on and see a second example with a non-terminating target. I want to log and then drop incoming SSH packets. In the same script, I'll log incoming SSH packets, so instead of accept, I will use the log target. This rule will log incoming SSH packets. And the second rule with the same matches will drop SSH traffic. I'm saving the script and running it. From Linux 2, I'll connect using SSH to Linux 1. We notice that SSH is not working. The packets were dropped by the second rule, not by the first one. The first rule has logged information about the packet headers, and then the packet continued traversing the chain and were dropped by the next rule. IP tables -vnl. I am listing the firewall. We notice that both rules have matched packets, and it's the same number. 6 packets have been logged and then dropped. The log target uses the kernel log facility. If we execute the message, like this, we'll see the logged packets. These are the headers of a logged packet. That's another proof that the packets have been logged and only then dropped. In this lecture, we'll see the accept and drop targets again. It's more like a recap because we've already used them in so many examples. Both accept and drop are terminating targets. If a packet is matched against a rule that has the accept or drop target, the packet is accepted or dropped and will not traverse the chain anymore. Let me show you an example. I want to permit incoming ping packets only from a management station or from a single IP address. Before getting started, I want to explain to you what ping means in case you don't know. Ping is a utility command available in any operating system, and it serves two primary purposes: to check if the destination host is available and to measure the round-trip time for messages sent from the originating host to a destination host that are echoed back to the source. According to Wikipedia, the name ping comes from active sonar terminology that sends a pulse of sound and listens for the echo to detect objects underwater. Ping operates by sending Internet Control Message Protocol or ICMP echo request packets to the target host and waiting for ICMP echo reply packets. So allowing ping means in fact allowing incoming ICMP echo request packets and outgoing ICMP echo reply packets. Let's see its help. IP tables minus P ICMP, the protocol is ICMP minus minus help. We notice that we specify the type of ICMP packet using minus minus ICMP minus type, and these are all available ICMP types. Among them, we see echo reply and echo request. In this example, I'll write IP tables rules only for the input chain, so for incoming traffic, but you can write IP tables rules for the output chains as well. So the first rule will allow incoming ICMP packets of type echo request if the source IP address is that of the management host. In this example, I'll consider the management host as being the Windows recording machine, which has the IP address 192.168.0.112. IP tables minus A input minus P ICMP minus minus ICMP minus type echo minus request minus S 192.168.0.112 minus J accept. And the second rule that will drop all incoming ICMP echo request packets if the source address is another host, not the management station. So IP tables minus A input minus PICMP minus minus ICMP minus type echo request minus J drop. In fact, it's the same rule without the minus S option, so without the source IP address. Let's test it. If a packet with the source IP address 192.168.0.112 is coming, it will be accepted by the first rule. Being a terminating target, the packet will not be evaluated by the second rule, which of course would drop it if it evaluated the packet. From the management station, I'm gonna ping Linux 1. And ping is working. Perfect. And I'm listing the firewall. And we see matched packets by the first rule. Now, if an echo request packet is coming from another IP address, the first rule will not match and the second one will drop the packet. Let's ping it from Linux 2. And we notice that Linux 2 is not receiving anything back. The second rule is dropping any echo request packets coming from another source IP address. There are 37 dropped packets by the second rule. To become proficient in firewalls and networking in general, you must know in great detail what are the states of UDP and TCP ports and how each type of port behaves when receiving a packet. Let's dive deeper into TCP and UDP port states. Basically, there are three types of ports: open, closed, and filtered. Let's take them one by one. What is an open port? An application is actively accepting TCP connections or UDP datagrams on an open port. Finding these ports is often the primary goal of port scanning. Attackers and pen testers want to exploit the open ports while sysadmins try to close or protect them with firewalls. Open ports are also of interest for non-security scans because they show services available for use on the network. You can see all open ports on your host by running the netstat command, which is available on Linux, Windows, and Mac. In the next lecture, I'll show you a few examples of how to use netstat. Let's see what is a closed port. There is no application listening on a closed port. Even though a port is closed, it's reachable. When sending a packet to a closed port, the port responds back to the source. They can be helpful in showing that a host is up. This is known as host discovery and is part of OS detection. When you send a TCP packet with the SYN flag set to a closed port, the port responds back with a TCP reset packet, and if you send a UDP packet to a closed port, the UDP port responds back with an ICMP packet of type destination unreachable and subtype port unreachable. Sysadmins may want to consider blocking such ports with a firewall, and they will appear in the filtered state. And the last state of a port is filtered, and it means that a firewall is blocking any packet to that port. A port scanner like Nmap cannot determine whether the port is open or closed because packet filtering prevents its probes from reaching the port. As a conclusion, a filtered port can be either open or closed. Filtered ports can be divided further into two categories: open filtered and closed filtered. A filtered port is also known as a stealth port. In this lecture, we've seen what are the states of a TCP or UDP port. In the next lecture, I'll show you how to check for open ports on your host and how to do port scanning on remote hosts. See you in a second. In this lecture and the next one, we'll take a look at two very useful utilities which are used to find information about ports. They are netstat and nmap. Let's get started with netstat. By the way, netstat comes from network statistics and on Linux is part of NetTools package. If you don't have the netstat command, you should install the NetTool package according to your distribution. For example, on Debian or Ubuntu-based distributions, you run apt update and apt install net-tools. On my machine, it's already installed. And I'll execute netstat -tupan. Sorry, it's netstat. The T option is showing TCP ports and U UDP ports. P comes from protocol, so it displays what protocol there is, TCP or UDP. A means all, and N comes from numeric. It displays ports in numeric format and not the service name. For example, we see 22 and not SSH. The output of netstat is showing both the listening ports on the host and active connections. So if I open a browser and connect to a remote web server, I'll see the connection in the output of netstat as well. There is a lot of output. You can filter it using a pipe and grep. For example, I want to see if SSH is listening or if port 22 is open, and I run netstat -tupan pipe grep 22. And we notice that SSHD is listening on port 22. 0.0.0.0 means that is listening on each IP address of the host. But if I'm searching for port 23, we see that there is no process that's listening on port 23. The netstat command is available in Linux, Windows, and Mac. However, on Windows, there are other options available. Most of the time, you'll simply run netstat -a. And it will display all open ports and active connections on the local host. Let's move ahead and take a look at Nmap, which comes from Network Mapper and is a network discovery and security auditing tool widely used by network administrators for many types of scanning. It's a complex open source application that maybe deserves its own dedicated course, in my opinion. There are a variety of scans that can be performed using Nmap. I want to mention just a few of them. TCP SYN scan is the default and most popular scan option for good reasons. It can be performed quickly, scanning thousands of ports per second on a fast network if there are no firewalls that restrict the scanning. It is also unobstructive and stealthy since it never completes TCP connections. This technique is often referred to as half-open scanning because it doesn't open a full TCP connection. Nmap sends a SYN packet as if it is going to open a real connection and then waits for a response. A SYN and an acknowledgement indicates that the port is listening, so it's open, while a reset indicates that the port is closed. If no response is received, the port is marked as filtered. Keep in mind that you need root privileges to perform this type of scan. If you don't have root privileges, you can still perform another type of TCP scanning called TCP Connect scan. Let's go to the terminal and see some examples. First, let's check if Nmap is installed by executing Nmap without any option. And it says command nmap not found and gives instructions about how to install it. On Debian and Ubuntu-based distributions, you can install it by simply running apt install nmap. And it's done. You can also install Nmap for Windows or Mac, and if you want a graphical interface, install ZenMap, which is the official Nmap security scanner GUI. This is ZenMap. Let's try a TCP SYN scan. If you are root, this will be the default scanning type. I'm root. Nmap and the IP address of the other Linux machine. And we see a lot of information about the scan and the destination host. We see how much time the scan took, the MAC address of the destination host, and the open ports. By default, Nmap scans the most common 1000 ports for each protocol, TCP and UDP. We see that 4 ports are open and 996 closed ports. If you are not root, you cannot perform this scan. I open up another terminal where I don't have root privileges and try to scan the host again, this time specifying -SS, which indicates a TCP SYN scan. Nmap -S, a lowercase s, and an uppercase S, and the IP address of the destination. And it says that I don't have the required privileges. What I can do is to perform another type of TCP scan called Connect Scan. This is the default for non-root users. I simply run nmap and the IP address of the destination. Or I can specify -s and an uppercase T. It's the same. Earlier I've said that by default nmap scans the most common 1000 ports for each protocol. What if a service has been moved to a non-standard port? Like SSH is listening on port 50,005. On the destination, let's change the SSH daemon listening port to 50,005. This is the configuration file of SSH daemon, and I'll write port and the new value, 50,005. That's the new port. I'm saving the file and then restart the service. Now SSH is listening on port 50,005. Nmap will not scan the port by default, and you cannot discover that the service is running. Let's scan the destination again. And we don't see that SSH is running. It didn't display the port as being open. In fact, it didn't scan the port at all. What I can do is specify the port manually using -p option. Let's scan the target again and specify the port manually. Nmap, -p, and the ports I want to scan. Let's say 20, 22, 80, and 50,005. And the destination, the same IP address. Perfect. Ports 20 and 22 are closed, and 80 and 50,005 are open. We see that the port is open, but it doesn't say who's listening on the port. What I can do now is add another option that does version detection, and that's -sv. So -sv, an uppercase V. And it's much better. It's displaying a lot of information about the services that are running on those ports. And if you want to scan all ports, you use -p- option like this. It's scanning all ports. By the way, this can take a very long time. If you press the Enter key while scanning, it will say what % of the entire scan process has been already performed. And it's done 5%. I'm stopping Nmap by pressing Ctrl+C. This was all about TCP scans. Other types of scans you can perform are UDP and ICMP scans. UDP port scanning is generally slower and more difficult than TCP. UDP port scanning is activated with the -SU option. Nmap -SU localhost. I'm scanning the localhost for UDP ports. And this is the result. And to perform an ICMP ping scan, use -SN or -SP. Nmap -SN. Both letters are lowercase. And I'll scan an entire network. And it has displayed information about all hosts that are up in this network. This is the local area network. Okay, that's all about Nmap for the moment. There's a lot of information about Nmap, but I think there are the most important things you should know. I'll attach to this lecture some resources about Nmap in case you want to dive deeper into it. Thank you. Now that you know in detail what are the port stakes, how to check what ports are open on the local machine, and how to scan ports on remote machines, I'll move ahead and talk about reject. Reject is another terminating target, and like drop, it denies the packet, but also sends back a reply packet to the source. By default, it replies with an ICMP port unreachable packet, and it's possible to specify the response packet using --reject -with option. Maybe you wonder why it's necessary to use reject when we have drop that silently drops any packet matched by the rule. And the answer is that sometimes it's more efficient to reject than drop packets because dropping packets will cause TCP to retry the connection until the threshold for the retransmission is reached. The retransmission timeout is generally of tens of seconds. By rejecting packets, TCP aborts the connection and the application gets to know that the connection has failed after just one round-trip time. Contrary to popular belief, drop does not give better security than reject. In this example, I reject forwarded or routed traffic that is going to port 69 UDP and I inform the source by sending back an ICMP port unreachable packet. You can see the options of the reject target by running iptables -j reject -help. Let's try some examples. I want to reject SSH traffic from Linux 2 to Linux 1. This is Linux 2 and this is Linux 1. On Linux 1, I will add an iptables rule that rejects SSH traffic from Linux 2. iptables -a input -p TCP -d port 22 -s the IP address of Linux 2. -j reject. I don't specify any reject options because I want you to see the default option. On Linux 1, I'll start TCP dump, and I want to capture all the traffic from Linux 2. TCP dump, host, and the IP address of Linux 2. -n. Perfect. Now, on Linux 2, I'll scan port 22 on Linux 1 using nmap. nmap -p22 and the IP address of Linux 1. And we notice that nmap reports the port as being closed. And on Linux 1, in the TCP dump output, we can see those packets. I'm stopping TCP dump by pressing on Ctrl+C. Let's look for the packets. There are many packets, but let's take a look only at these two packets. Server 2, ending in 20, is sending a TCP packet with the SYN flag set to Linux 1, ending in 10. Here, this is the packet. The packet is dropped, and then Linux 1 is responding back with an ICMP packet to Linux 2. The ICMP packet is the default, which is port unreachable. And if I list the firewall, I'll see dropped packets. There is only one packet dropped by the rule. This packet. Now, I'll add the same iptables rule, but this time I'm using -i instead of -a. This rule will be the first rule in the chain and the rule that will match the packages. The previous rule will be deactivated because no package will be ever been matched against it. And I want to specify what packet will be sent back to the source after dropping the incoming SSH packet. And I want a TCP reset. So minus minus reject with TCP minus reset. I'm starting TCP dump again. And I'm scanning port 22 again. The port is reported again as being closed. Let's take a look at TCP dump output. I'm stopping TCP dump. Let's look for the packets. These are the packets. We see how server 2 has sent a TCP packet with the SYN flag set, and in response, server 1 has sent to server 2 a TCP packet with the reset flag set. This is the response. Okay, one more check. I'll add this rule one more time, but this time I'm using the drop target instead of reject. This rule will be the first rule on the input chain, so it will match the packets. Drop. I'm starting TCP dump again and scanning Linux 1 again. Now the port is being reported as being filtered. That's because nothing is received from Linux 1. Let's take a look at the output of TCP dump. We can see that Linux 2 has sent SSH packets to Linux 1, which silently discarded the packets without responding back to the source. In fact, Linux 2 has sent 2 packets to Linux 1 and after that gave up entirely. Hello guys! In this video, I'll cover the log target. We've seen a lot of terminating targets like accept, drop or reject. We'll shift our focus to a commonly used non-terminating target named log. If a packet is matched against a rule with the log target, the packet headers are logged, and then the packet continues to traverse the chain rules until it is accepted, dropped, or rejected by a rule or by the default policy. Log target is specially designed for logging detailed information about packet headers. It does this via the kernel logging facility. This information can then be read directly with dmessage or from the syslog daemon logs. Note as well that it could be a really great idea to use the log target instead of drop while you are testing a rule and you are not 100% sure about it on a production firewall. A syntax error in the rule sets could cause severe connectivity problems for your users. The log target takes 2 options that could be of interest: minus minus log minus level and minus minus log minus prefix. Log level indicates the priority or severity of the logged message, and log prefix tells IP tables to prefix all log messages with a specific prefix or string, which can then be combined with grep to track specific problems and output from different rules. Let's see an example in our testing environment. I want to log and then drop the first packet of any incoming SSH connection, the packet that establishes a new connection, by initializing the TCP three-way handshake. That's the packet that has the SYN flag set. IP tables -a input -p TCP -d port 22 -SYN. That's the first packet of the connection -j log. And -log prefix equals, between double quotes, incoming SSH traffic. And the other option, -log -level info. Log target is a non-terminating target, and that means that the matched packet continues to traverse the chain. My second rule will drop the packet IP tables minus A, input minus PTCP, minus minus dport 22 minus J drop. From Linux 2, I'll try to connect using SSH to Linux 1. The connection is not working because the packet that initializes the connection is locked and then dropped. On the firewall, I'll execute the message to see the kernel logs. These are the kernel logs. Among these logs, we notice the logged packets. We see the log prefix, which is the string incoming SSH traffic. There are a lot of messages, so it could be a good idea to select only the messages we are interested in, and we can do that by using a pipe and the grep command. The message pipe grep, and I want to see only the lines that contain incoming SSH traffic. SSH traffic is enough. And we are seeing only those rules. If I want, I can also redirect these lines to a text file for later inspection. I'm using the output redirection. ssh.txt and cut ssh.txt. We see the logs in the file. The message is only displaying a buffer in the RAM memory. If you want to see the logs after the computer restarts or at a later moment, you should read from a specific log file. Based on the Linux distribution you are using, the logs are saved in a specific file on your file system. On Ubuntu, the kernel logs are saved in /var/log/kern.log. Let's see the file using the tail command. Tail -f var log kern.log. -f option means that it will display the tail of the file in real time as data is appended to the file. By the way, tail is displaying the last 10 lines by default. I'm connecting to port 22 on Linux 1 again. And we notice how the contents of the log file is updated in real time. Note that the log target doesn't save the packet contents, it only saves the packet headers. If you want to save the packet contents, you should use a packet sniffer like tcpdump or Wireshark. The T-target will clone a packet and then redirect that cloned packet to another machine on the local subnet. It's used for traffic mirroring. In this example, I clone and redirect all routed traffic to destination 80.0.0.1 to my gateway, which has the IP address 10.0.0.10. Let's see a live example. I want to clone and then redirect to Linux 2 all ICMP ping packets from the Windows machine destined to Linux 1. On Linux 1, I write IP tables -a input -p ICMP -ICMP -type echo request. These options will match incoming ping packets -j t --gateway and the IP address of Linux 2. On Linux 2, I'll sniff all ICMP traffic using tcpdump. I want to see the ICMP echo request packets. tcpdump -n. OK, I have to be root. I'll prefix the command with sudo. And from Windows, I'll ping Linux One. Ping and the IP address of Linux One. Perfect. Ping is working. We notice that packets destined to Linux One, this is Linux One, are received also by Linux 2. That's mirrored traffic. If I list the firewall, I notice many matched packets by the rule that uses the t-target. There are 4 matched packets. 4 packets have been cloned and then redirected to Linux 2. In this lecture, we'll see the redirect target, which is used to redirect packets from one port to another on the same machine. The redirect target is extremely useful for setting up a transparent proxy where local area network hosts do not know about the proxy at all and are forced to go through the proxy. The redirect target is valid only within the pre-routing and output chains of the NAT table. Let's see how it works with a live example. On Linux One, I want to redirect traffic that's coming to port 1234 to 22, where the SSH daemon is listening. IP tables -t NAT. The redirect target is available only on the pre-routing and output chains of the NAT table, -i pre-routing. The rule will be added to the pre-routing chain, and now the matches -ptcp -d port 1234 -j redirect -2 ports 22. Let's check if port 1234 is open on Linux One. netstat -tupan pipe grep 1234. And it's not open, it's closed. From Linux 2, I'll connect to Linux One using SSH and port 1234. SSH -p from port 1234 and the IP address of Linux One. And we notice that it's connecting to port 1234 even though there is no application listening on that port. What's happening? Packets that arrive on Linux One and port 1234 are redirected when hitting the pre-routing chain to port 22, where the SSH server is listening. This was just a simple example to show you how it works, but on port 22 could listen a special application that performs application filtering and inspection like Squid or other proxy does. In this section, we'll dive deeper into NAT or masquerade. What is NAT? NAT comes from network address translation and is the process of rewriting the source or the destination IP addresses of the packets as they pass through a router or firewall. Simply put, NAT enables private IP hosts to connect to the internet. There are two kinds of NAT: SNAT or source network address translation and DNAT or destination network address translation. SNAT replaces the private IP address from the packet with the public IP address of the router external interface. NetFilter framework enables a Linux machine with an appropriate number of network cards or interfaces to become a router capable of SNAT. SNAT always uses the NAT table and the post-routing chain. You'll sometimes hear the term masquerade. What is masquerade? It's a special case of SNAT used when the public IP address of that NAT router is dynamic. It will automatically take and use the IP address of the outgoing network interface for network translation. We use Masquerade when there is a DSL, coaxial or fiber internet connection with a dynamic IP address. When configuring the Linux machine for SNAT or Masquerade, the NetFilter framework also performs port address translation or PAT. It means that it will translate the source port of the packet as the packet is routed. Let's see how we configure SNAT or Masquerade. The first step is to enable the routing process on the Linux machine. By default, routing is disabled in Linux, and there are two possibilities. The first possibility is to write the value 1 in a special file. 1 means routing enabled, and 0 means routing disabled. It's common to use the echo command and a redirection like this. Echo 1, output redirection, //proc/sys/net/IPv4/IP_forward. The second possibility is to edit a file named sysctl.conf from the etc directory. And inside that file, we add net.ipv4.IP_forward equals 1. After editing the file, it is required to restart the network service. It can depend on your Linux distribution, but for example on Ubuntu-based distributions, you execute systemctl restart networking. If you enable the routing process using the first way, which is writing 1 to IP_forward file, it's not required to restart the network service. That was the first step. The second step after enabling routing is to configure SNAT or Masquerade. Add an IP tables rule to NAT table and pre-routing chain that matches packets that should be netted. Specify the external interface using -o option and use -j SNAT --to source and the public IP address of the router's interface, or -j and Masquerade as target. Let's look at an example. First, we enable the routing process and then we add a rule to NAT table and post-routing chain that translates all packets that have the source IP address from the network 10.0.0.0/24. The source IP of the packets will be translated to source 80.0.0.1, which we'll suppose is the public IP address of the router. Or instead of -j SNAT --to source, we could simply use -j Masquerade, and NetFilter will automatically take and use the public IP address of the given interface. In this case, ETH0. That's all. In the next lecture, we'll configure together a Linux machine to be router and perform NAT. In this lab, we'll configure NAT from scratch on a Linux machine using NetFilter and IP tables. This is our topology. This is my Windows recording computer that's connected to the NAT router using an Ethernet connection through a layer 2 switch. The NAT router runs Ubuntu and is connected directly to the internet using a wireless connection. The name of its external interface is WLO1 and the name of its internal or LAN interface is ENP8S0. You can see the names of the Linux interfaces by running ifconfig command. Yes, I know, these names are difficult to remember, but we don't give them too much importance and take them as they are. The LAN network address is 10.0.0.0/24. The Windows PC has 10.0.0.2 and the Linux router has 10.0.0.1 on the internal interface. The public IP address, which is the IP address of its external interface, is dynamic and it's not important to us. On Windows, on the Ethernet interface, I'll set a static IP. 10.0.0.2, the subnet mask will be 255, 255, 255, and 0, it means /24, and the default gateway will be the IP address of the net router, 10.0.0.1. And the DNS server will be the public DNS server from Google. Perfect. Let's get started with the net configuration. I'm gonna connect using SSH and PuTTY to the Linux net router. There is another wireless connection between Windows and Linux router, connection that will be disabled at the end. I'm using it only for this configuration. This is the net router and I've become root. All iptables commands should be run by root only. The first step is to enable the routing process on the Linux net router. Echo 1, the output redirection, /proc sys net IPv4 /IP_forward. Now the Linux machine is a router. The second and the last step is to create an iptables rule that matches traffic that will be netted. Keep in mind that we should always use the net table and the post routing chain, and the target will be snet or masquerade. We use snet when we know the public IP address of the router, that's a static address, and masquerade when the public IP address is dynamic and it changes frequently. That's a dynamic IP address. iptables -tnet -a post routing -s the entire subnet 10.0.0.0/24 -o the outgoing interface, the external interface of the router, WLO1 -j masquerade. By the way, it's not mandatory that all LAN traffic, like in this example, to be netted. It's possible, for example, to net only DNS, email, HTTP, and HTTPS traffic. We use the required matches. Okay, that's all. Let's check if it's working. On the Windows machine, I'm going to disable the wireless interface. I should be able to access the internet using the Ethernet connection and the net router I've just configured. So, disable. Good, it's disabled. I'm opening the command prompt cmd.exe and then test the layer 3 connection to an external IP address like, for example, 8.8.4.4. By the way, this is another public DNS server from Google. And it's working. The packets have reached the Linux router, which has translated the source IP address with the IP address of its external interface and sent them to the destination on the internet. I'm opening a new connection to the net router and then I'll list the net table. By the way, the first SSH connection froze. So 10.0.0.1 and here I have a custom port 2299. And it's working. I'm authenticating. and I'm becoming root. IP tables minus tnet minus VNL. We notice that 31 packets have been matched and translated by the rule. Also keep in mind that the configuration is not saved after the system is restarted. If you want to activate net at boot time, you should write the configuration inside the script and set the script to execute it at boot time automatically. In this video, we'll talk about DNet, which comes from Destination Network Address Translation, aka port forwarding. Destination Network Address Translation or port forwarding is a technique that allows connections from the internet to servers with private IP addresses inside LANs. The internet client connects to the public IP address of the DNet router, which in turn redirects the traffic to the private server. The private server, which has a private IP address, stays invisible all the time. The clients from the internet do not know that they are not connecting to the server with the public IP address, which is the router, and that are connecting to another server in a LAN. DNet uses net table and pre-routing chain, and the IP tables rule target DNet. Let's go to the terminal and configure DNet or port forwarding on the net router. In this example, there is a web server running on a private IP address which is 10.0.0.2, and the net router has the private IP address 10.0.0.1 and the public IP address 80.0.0.1. Port forwarding means that users from the internet can communicate with the web server that has the private IP address. As I've already explained, they will connect to the public IP address of the router, which in turn will change the destination IP from 80.0.0.1 to 10.0.0.2 and then forward the traffic to the private web server. SNet is assumed already configured and it's working properly, meaning that traffic from the web server to the internet clients goes through the net router. You can take a look at the previous lecture to see exactly how it's done. Enough talking, I'm writing the IP tables rule. IP tables minus tnet, I must use the net table and the pre-routing chain, minus a pre-routing. And the HTTP traffic, so p TCP minus d port 80, minus j dnet, and minus 2 minus destination, and the IP address of the web server, 10.0.0.2. That's all. Now, traffic that is coming to 80.0.0.1 with the destination port 80 and protocol TCP will be translated and forwarded to destination 10.0.0.2. Another possibility is to specify another port as a match. Let's say 8080. And :80 here after the private IP address. How will it work? Traffic that's coming to 80.0.0.0.1 and port 8080, so the client is connecting to port 8080, will be forwarded to 10.0.0.2 and port 80. Also keep in mind that the configuration is not saved after a system restart. If you want to activate port forwarding at boot time, you'll write the configuration inside the script and set the script to execute it at boot time automatically. Now that you know how to configure NAT on a Linux router, let's do a small project that can be very useful. Suppose your LAN is connected to the internet using two different service providers. The net router is running Linux. Your task is to create a script that configures the net router to load balance outgoing routed traffic in the following way. SSH, email, and web traffic will use the first connection, so the first ISP, and all other traffic will use the second service provider, ISP2. One important remark is that internet traffic is asymmetric. That means that we cannot force a router to select a specific route. What does it mean? It means that even though we send traffic using the first connection, traffic could return back through the second service provider. Okay, these are the project requirements. In the next video, I'll show you how I would do it in case you get stuck. Good luck! This lecture is the answer to the assignment given to you in the lecture prior to this one. This is just a recording of me thinking loud and walking through the assignment. Maybe you took another approach and that's fine as long as you get the end result. I'm gonna create a script called loadbalancenet.sh. The first line is the shebang. Let's define what services I'm gonna configure for net using the first ISP connection. And there are the following services and their ports. So there is web, and that means 80 and 443, these two ports. Another service, email, and there are more ports, 25 for SMTP, 465 for SNTPS, 143 for IMAP, 993 for IMAP-S, 110 for Post Office Protocol, POP, and 995 for POP-S, so POP over SSL. And there is also SSH that uses port 22. Perfect. I want to remain flexible, so I'm creating a variable that contains the ports. It's easier to add or remove a port in the future this way. And the name of the variable will be ISP1 equals, and the ports between double quotes and spaces between them. So 22, 25, 80, 110, 143, 465, 993, and the last port 995 for POP-S. This is the traffic that will use ISP1. The next step is to flash the net table of post-routing chain. When I run the script, it will start each time from scratch. So IP tables minus tnet minus f post-routing. Good. The first step is to enable the routing process on the Linux machine. Echo 1, and I'll redirect the value 1 to a specific file. And the file is /proc sys net IPv4 and IP forward. Now the Linux machine is a router. Okay. Using a for loop, I'll iterate over the previous declared variable and write a rule for each port in that variable. So for port is a temporary variable. I can use any name I like, in, $, and the name of the variable, ISP1. Do and done. And between do and done, I write the IP tables rule that performs snet. Let's check what will be the outgoing interface. In this case, it's ETH1, Ethernet 1. You should change it according to your own topology. You see the name of the interface by running ifconfig. And the IP tables rule, IP tables minus tnet minus a post routing minus ptcp minus d port port, the temporary variable of the for loop, minus O, and the outgoing interface, ETH1 minus J masquerade. I'm using masquerade and not SNAT because I don't know the public IP address of the router. Maybe it's a dynamic one. This is enough for the first connection, for ISP1. Another rule is required that will masquerade all other types of traffic through the second connection. So if a packet was not translated until this point, and this means using ETH1 and the first ISP, it will be source translated and sent over the second connection. So using the interface called ETH2. So IP tables minus tnet minus A post routing minus O ETH2 minus J masquerade. Okay, that's all. I am saving the script, then make it executable and run it. I'm listing the net table, IP tables minus tnet minus VNL. Okay, and we see here all the rules. This was my solution to the assignment given to you in the last lecture. Hello guys and welcome back. In this lecture, we'll talk about a more advanced topic called user-defined chains or custom chains. By default, the IP tables filter table consists of 3 chains. There are input for incoming traffic, output for outgoing traffic, and forward for routed traffic. Besides these 3 built-in chains, you can add as many other custom chains as you like in order to simplify managing large rule sets. We can create a very good firewall without user-defined chains, just that user-defined chains are useful in optimizing the rule set. They allow the rules to be organized in categories, and this way the firewall becomes scalable. Custom chains behave just as built-in chains, introducing logic that must be passed before the ultimate fate of a packet is determined. From a built-in chain like input, output or forward, using -J and then the name of the custom chain, you can jump into any number of user-defined chains and even jump between them. The matched packet traverses the user-defined chain, and after that the control is returned to the calling built-in chain and matching continues from the next rule in the calling chain. This was the logic of user-defined chains or custom chains. Let's talk about the return target. If there is a match in a custom chain and the target of the rule is return, the processing of the packet resumes back immediately in the main built-in chain that called the custom chain. The return target can be used also inside the built-in chains like input or output, and in that case no other rule will be inspected and the packet executes the default policy of the chain, which is either accept or drop. Custom chains introduce many ways of optimizing things. Like say you want to stop using the rules of a custom chain temporarily without deleting the chain. You simply delete the jump from the main built-in chain to the custom chain. Let's take a look at available options. -N creates a new user-defined chain and -X deletes a user-defined chain. To list the rules of a user-defined chain, you use -L as usual. Note that before deleting a user-defined chain, the rules of the chain must be flushed or you get an error. To flush the rules of a user-defined chain, you use IP tables -F and the name of the chain. This was just an introduction to custom chains. In the next lecture, I'll show you how to implement and use custom chains. See you in a second. Let's go to the terminal and take a look at some examples. iptables-vnl lists the default built-in chains of the filter table. There is input, output, and forward chains. Now let's create a new chain called myChain. iptables-n, an uppercase N, and the name of the chain, myChain. Now, if I list the filter table, I see all the built-in chains plus the user-defined chain called myChain. Let's add an iptables rule to myChain. iptables-a myChain and the matches -p ICMP -ICMP -type echo request -j drop. This rule will drop all incoming echo request or ping packets. At the moment, the rule exists, but it's disabled because there is no jump to myChain from a built-in chain. I'm gonna test this by sending ping packets from Linux 2 to Linux 1, ping, and the IP address of Linux 1. And we notice that ping is working. Echo request packets are still accepted by Linux 1. Back on Linux 1, I will enable myChain. How will I do this? From the input built-in chain, I'll jump to myChain. iptables-a input -j myChain. And we notice how ping has stopped. That's because the rule from myChain has been activated and packets are matched and dropped by the rule. Let's dive deeper into how it works. The packets traverse the input chain, and if they are not dropped or accepted by a rule, they jump into myChain. In this case, there are no other rules on the input chain that could drop or accept them, so they start traversing the custom chain, which has only one rule that drops the packets. If the packets hadn't been dropped, they would have returned to the input chain and would have continued traversing the input chain until a rule drops or accepts them or the default policy is executed. If I'm listing the firewall again on Linux 1, we notice 121 matched packets by the rule of myChain. These are dropped ping echo request packets. But if we take a look at the rule of the input chain, we see a larger number. 145 packets have traversed the user-defined chain. The number is larger because not only ping packets traversed the user-defined chain, but all incoming packets. Or simpler said, 145 packets traversed the input chain and then myChain, and 121 of them were of type echo request and dropped by the rule of myChain. If I want to delete myChain, I use iptables -x and the name of the chain, myChain. Let's try it. And I've got an error. I cannot delete a chain that has rules. So first I must flush the rules of the chain. iptables -f myChain. And by the way, ping has started again. Now there is no rule that drops the incoming ping packets. If I list the firewall, I notice that there is no rule in the chain. Let's try to delete the chain again. IP tables minus X and the name of the chain. And I still have an error. Why is that? That's because there is a reference to this chain from the input chain. As a conclusion, we cannot delete a user-defined chain if the chain has rules or if another built-in chain is referencing the user-defined chain. So in order to delete the custom chain, I must first delete the rule from the input chain that references the custom chain. IP tables minus F. I am flashing all the chains. There is no reference to my chain and I can delete it. IP tables minus X, my chain. By the way, if I execute IP tables minus X, so without the name of the chain, it will delete all user-defined chains. Let's see an example where a user-defined chain is created and used in order to have a more organized and scalable IP tables firewall. To save time, I've already created this firewall script and will refactor it together using user-defined chains. This is the script. For the beginning, let me explain to you what this firewall script does. After flashing all chains of the filter table, I allow outgoing or generated packets that are in new, established or related states. These are in fact all packets except invalid ones. Then there are two rules. One rule that allows incoming SSH traffic from any source to our Linux machine, and another rule that allows the return generated traffic. This means that anyone is allowed to connect to this Linux machine using SSH if the user has the right credentials. And I also permit 4 MAC addresses, so 4 hosts from the same LAN, to initiate connections to the Linux host. And finally, I set the drop policy on both input and output chains. Any packet that was not matched and accepted by a previous rule will be dropped. Now, let's see how we can refactor this firewall script to scale well in case that instead of 4 MAC addresses, there will be 50 MAC addresses. I also want the possibility to switch on and off all rules related to MAC addresses. Let's get started. I will create a user-defined chain. I could create the chain accepted MAC, and instead of adding these 4 rules to the input chain, I can add these rules to my new user-defined chain, and then I will jump from the input chain to my user-defined chain. If the packets will not be accepted by a rule of the new chain, they will continue traversing the input chain for further processing. Okay, let's do it. I'm creating a user-defined chain called accepted MAC. IP tables minus n accepted underline MAC. Alright. And I add these rules to my new chain accepted MAC. The first rule, the second rule, and the last 2 rules. Okay. Now I must jump from the input chain to my newly created chain called accepted MAC. IP tables minus a input minus j accepted MAC. And one last thing, at the beginning I want to delete any user-defined chain. IP tables minus x. So each time I'm starting from scratch. Okay, that's all. Let me explain to you in detail what will happen with the packets. I think everything is clear for outgoing traffic. I'm accepting all outgoing traffic except invalid packets. Then, if an incoming packet is of type SSH, it will be accepted. If a packet was not accepted nor dropped, it will further traverse the accepted MAC chain. And if the source MAC address is one of these four, the packet will be accepted. If not, it will continue traversing the input chain. In this case, there is no other rule in the output chain, and the packet will be dropped. I am saving the file, making it executable, and running it. We can see the user-defined chain. There is one reference to it. Here, on the input chain, there are already 4 packets that have traversed the chain, but no packet was matched against a rule of the chain. Now, if I want to disable all the rules related to the MAC addresses, I simply comment out the rule where the jump is made. So this rule. Instead of deleting these 4 rules, I have just commented out this single rule. This is one of the advantages of using user-defined chains. This lecture is a very important one, and maybe it's a good idea to bookmark it for future reference. In order to write efficient firewall rules, you must deeply understand how a packet traverses the net filter tables and chains. A packet can be found in one of the following scenarios. It comes from the network and is destined for our host, which is the final destination of the packet. In this case, the packet traverses the pre-routing and then the input chains. The second scenario is when it comes from the network, but it's not destined for our host. In this case, our host is not the final destination of the packet. The packet must be routed or forwarded by the Linux machine, which is the router in this case. The packet traverses the pre-routing, forward, and then the post-routing chains. And the last scenario is when the packet is generated by an application on the host. The local Linux machine is generating the packet. In this case, the packet traverses the output and the post-routing chains. Let's move on and have a closer look at a packet that is destined for our own local Linux machine. It would pass orderly through the following steps before actually being delivered to the application, client or server, that should receive it. When a packet first enters the firewall, it hits the hardware and then gets passed on to the proper device driver in the kernel. The bits of the physical layer are transformed into a data frame and then into a packet. After that, the packet starts to go through a series of steps in the Linux kernel before it's either sent to the correct local application, client or server, or dropped. The packet starts traversing the rules from the route table of pre-routing chain. This is where connection tracking takes place, and in this table and chain we add rules that match packets that should skip the connection tracking system. Then the packet traverses the mangle table of pre-routing chain. At this point, we can change values from packet headers like type of service bigs or time to leave. The net table of pre-routing chain is used for destination network address translation or port forwarding. Any traffic filtering should be avoided here. After the net table of pre-routing chain is traversed, it comes the routing decision. The Linux kernel should decide if this host is the final destination of the packet or it should be routed to another host. If this host is not the final destination, the packet will be routed and it gets to mangle table and forward chain. We'll dive deeper into this in another lecture. But if this host is the final destination, the packet starts traversing the mangle table of input chain. Here we can change values from the packet headers if we haven't already done that on the mangle table of pre-routing chain. After this step, the packet starts traversing a very important table and chain, which is the filter table of input chain. This is where we perform filtering for all incoming traffic destined for the local Linux machine. All incoming packets destined for the local host will pass through this chain, no matter via which interface or direction they came from. Filtering means accepting or dropping the packet. If the packet is not dropped, it goes to the local process, the client or the server application. This could be, for example, a web browser like Firefox or a server application like Postfix, Nginx, or SSH daemon. That's all. This is how all incoming packets are inspected against the rules of IP tables, tables, and chains. In this lecture, we'll take a deeper look at how outgoing or generated packets traverse the net filter tables and chains. First, the packet is created by the local process, the client or the server application. Then, it starts traversing the rules of the raw table of the output chain. Here, there are rules used to skip the connection tracking system of NetFilter. After that point, the packet traverses the rules from the mangle table of the output chain. At this point, we can change values from the packet's header, like time to leave or type of service. At the next step, the packet starts traversing the net table of the output chain. Here we can write rules that translate or change the source IP address of the packet. NAT takes place also on post-routing chain, but through post-routing chain goes also routed or forwarded traffic. So maybe we want to have different NAT rules for generated packets than for routed packets. After that point, at number 5 on the scheme we are looking at, comes a very important table, the filter table of the output chain. Here we perform filtering, which means dropping or accepting outgoing traffic. It's very important to filter also outgoing traffic, not only incoming traffic, because we don't want possible malware or rootkits to communicate outside our network. After the packet traverses the filter table of the output chain, the Linux kernel checks if the packet is routable, or if the IP destination is in the routing table. If it's not routable, the firewall drops the packet. But if the packet is routable, it starts then traversing the mangle table of post-routing chain. Here we can change other values of the packet's headers, and then the packet starts traversing the NAT table of the post-routing chain. Also here we define rules for source network translation or masquerade. If the packet has reached this point, the driver of the network interface, which is wireless or wired, transforms the packet into a data frame, and then the physical layer packs the frame into bits and sends the bits on the physical medium. Okay, that's step by step how outgoing or generated traffic traverses the tables and chains of NetFilter. In this lecture, we'll see in great detail how routed traffic traverses the tables and chains of NetFilter framework. We are assuming that the packet is coming from the network and is destined for another host on another network. First, the information is on the medium, wireless or wired in form of bits. Then, the interface driver transforms the bits into a data frame and then into a packet. The packet starts traversing the route table of pre-routing chain. This is where connection tracking takes place, and in this table and chain we add rules that match packets that should skip the connection tracking system. Then the packet traverses the mangle table of pre-routing chain. At this point, we can change values from the packet headers like type of service or time to leave. The net table of pre-routing chain is used for destination network address translation or port forwarding. Any traffic filtering should be avoided here. After the net table of pre-routing chain is traversed, it comes the routing decision. The Linux kernel should decide if this host is the final destination of the packet or if the packet should be routed to another host. Okay, if this host is the final destination, then this is an incoming packet and it goes to the mangle table of the input chain. In a previous lecture, we've already seen what happens in this case. But if the Linux machine is not the final destination, the packet must be routed, and it starts traversing the mangle table of the forward chain. After that, the packet starts traversing the filter table of the forward chain. This is a very important place where we add rules for filtering routed traffic. Here we decide what kind of traffic is allowed from the LAN to the internet and back. The next step, if the packet is not dropped, is to start traversing the mangle table of the pre-routing chain. We can change here values of the packet's headers, and then the packet starts traversing the net table of post-routing chain. Here we define rules for source network address translation or masquerade. If everything is okay and the packet hasn't been dropped until this point, the packet leaves our Linux machine. The driver of the network interface transforms the packet into a frame, and the physical layer transforms the data frame into bits and sends these bits on the medium. Okay, that's how routed or forwarded traffic traverses the tables and chains of NetFilter step by step. Thank you. Now I will explain some basics about Bash shell scripting. First, a shell script is a text file that contains commands and other programming structures like variables, loops, and so on, and can be run. A shell script is created using the preferred text editor like VI, Nano, Pico, and so on. For example, I use VI or VI improved. Let's create a script. Script1.sh. The first line of a shell script starts with a hash sign, then comes an exclamation mark, and then the absolute path to the program that executes the script. In our case, it's the bash shell, so bin bash. This is the absolute path on Ubuntu server. We can define variables only by specifying their names, for example IPs, and now between double quotes I can have a value, a string value. For example 129.66.3.4, 10.0.0.1, 5.5.5.5, and so on. Okay. We can get the value of the variable by putting the $sign in front of the variable name. For example, the value of variable IPs is $IPS. If we want to run the script, first we must save it, then we make it executable by specifying at least 700 as a permission. And now we can run the script specifying its relative path. This means dot the current directory slash and the name of the script. As you can see, the line number 5 brings the value of the variable IP as is, and then it replaces the name of the variable with its value. Pay attention that you can't execute the script simply by its name, like script1.sh. The bash shell doesn't look for the script inside the current directory, so it doesn't find the script. We get the command not found error. So we execute the script using // and the name of the script. Okay, we can execute the script also using its absolute path, like this, but it's easier to use the relative path. Inside the script, we have some predefined, some built-in variables. These are $1, $2. Let's see what they contain. For example, I write $1 is $1. If I want to cancel the special meaning of the $, I put a backslash in front of the $. Now, the $sign is not a special character, it's the $literal. So line number 7 will print $1 is and then the value of $1. I copy paste this line and I replace $1 with $2 with $3. Another built-in variable is $hash. We'll see what it contains in a minute when we'll run the script. Backslash $hash is $hash. There are more variables, but for this moment, these are enough for us. If we want to program a for loop, for example, we want to iterate through this variable, through IP's variable, we can simply run for IP in $IPs do done, and between do and done I have a block code with instructions. For every iteration, the variable IP has a value from the IPS list of variables, where the space is the separator. So if I write echo IP has or is $IP, what is the script going to print? It will print the first value till space, the second value, the third value, and so on. And if we want to test the value of a variable, we simply use the if construction. So if square bracket, and now for example $1 minus EQ equals, for example, 55. This means if the value of the built-in variable named $1 equals 55, then execute the following lines. I have just one line. $1 is 55. Else echo backslash $1 is not 55. Fi closes the if. We can talk more about bash scripting, but for our following examples, this is enough. Okay, I save the script. Now I run the script. 1, 2, 3, 4, 4, 4, XX. Okay, what do we see? First let's display the value of the script. So the value of variable IPs is, and I printed the value of the variable, then $1 is the first argument of the script. The first argument is the script, is the string that comes after the script name. So 1, 2, 3 is the first argument. Then 444 is the second script argument, and XXX is the third script argument. $hash contains the number of arguments. We have 1, 2, 3 arguments. $dash is 3. We don't have a fourth argument because we have only 3 arguments. That's why $4 is empty. Okay, and after that, this is my for loop. I iterated through that variable, through IP's variable, and I printed each time a value from that list. And my if test, it verifies if the first argument equals 55. My first argument is 1, 2, 3, so it doesn't equal 55. So it prints $1 is not 55. If I run the script one more time, 55, something like that, it prints $1 is 55. The last thing I show you in this lesson is how to read a variable from the standard input or from the keyboard. Let's take another example. Echo -n, -n makes the cursor to remain on the same line. And now enter something. Read my variable. Echo, you entered my variable. What happens? The third line prints at the terminal enter something, then on the fourth line a variable named my variable is created, and the value the user enters at the terminal will be allocated to that variable. So the variable will have the value that the user entered at the terminal. And on the line number 5, the script prints you entered and the value you have just entered. Let's test it. Read variable, the script stopped and waits for the user to enter something. This is just an example. You entered, this is just an example. Or, one more time, 6.5.3.56. You entered 6.5.3.56. In this lecture, I'm going to show you how to automate some IP tables tasks using shell scripts. Let's suppose we noticed some strange activities in our server logs, or maybe we seen some IPs that try to scan our server, or we received many spam emails from an IP or from a network address, and we want to block all incoming packets from that IP address. What is interesting is that we can automate this task. More interesting and useful is that a user that doesn't know much about IP tables and Linux firewalls can simply run the script blocking packets from that IP address. The user doesn't need to know about commands, rules, about ports and so on. He just runs the script and packets from that IP address will be blocked. Let's see an example. On server 1, I'll create a script that blocks incoming traffic from the IP address that is specified as the first argument of the script. I create a script named block_IP, block_IP.sh. The first line indicates that this script will be run by bash. Using echo, I write at the terminal dropping traffic from $1. As we've seen in the previous lesson, $1 means the first argument of our shell script. And now the IP tables rule. It is very important to add this rule using -i, not -a. Maybe our firewall already has many rules, and maybe there is a rule that permits traffic from that IP address or from the protocol that IP address is using. So it's important to add a rule that will be the first rule in the chain. So IP tables -i input -s, and now I write $1. $1 means the first argument of the script. The script will be called using the IP address, the offending IP address, as the first argument, -j drop. I save the script, I make it executable, and now on server 2, let's suppose we want to block the connection, the packets from server 2. Let's check that the connection between server 2 and server 1 is up. I will ping server 1 from server 2, so ping and the IP address of server 1. Ping works. And now back on server 1, first I check the firewall. Maybe I have some rules. Okay, I have some rules. It doesn't matter what they do. I'm not interested because my rule will be the first. So the packets will be dropped. Block IP, and now the IP address of server 2. Ping stopped. Packets from server 2, no matter of protocol, will be dropped. Let's see the firewall. The line that was added by the shell script is the first line on the input chain and already dropped 14 packets. One interesting thing is that we have another rule. This is the first, second, third, the fourth. We have the fourth rule that accepts any packets from any IP address inside my local area network, also from server 2. But because my line is the first, will drop the packets. Now I want to optimize the script. What if the user calls the script without an argument? So he calls the script like that, block IP, and presses enter. We get an error because you ran the IP tables command without the -s match. So inside the script here, we must specify the value of the source IP address. And if we run the script without an argument, $1 is empty. What can we do? There is another built-in variable named $hash that contains the number of arguments. I must verify that the script was called using one argument. So if $hash equals 1, then I run these 3 lines, this block of code. Else, echo, this script must be run with an argument, or better, with the blocked IP address as argument. Okay, I close the if using fi, I save the script, and now run it one more time without an argument. And we can see we got no error because the line number 10 was executed. So the else branch was executed because $hash is not 1. If I run the script using an argument, for example 3.0.0.0/8, I blocked the entire network address space. Let's see another example. Let's suppose we want to block access to a specific service that runs on our server. For example, we want to block connections to port 22 or to port 25 or to port 80 or whatever port we want. I create a script, block service.sh, echo blocking $1 port $2. $1 is the first argument of the script, $2 is the second argument of the script. The first argument of the script will be the protocol, for example TCP or UDP, and the second argument of the shell script will be the port, because we can block a TCP or an UDP port. IP tables -i, it's very important to specify -i. My rule must be the first, otherwise other rules could permit that traffic. -i input -p $1 -d port. The packet is coming to my service $2 -j drop. Echo done. And because we already know how to check that the script was run with the correct number of arguments, we write here we have 2 arguments then, and we have this code block. It's easier to follow what happens if we indent the code. Okay, else echo the script was run with the wrong number of arguments. Okay. We make the script executable. I want to permit again the traffic from server 2 just to test my second script. So IP tables minus I input minus S and the IP address of server 2. Okay, ping started. And now from server 2, I want to check if port 22 is open. So nmap minus p22 and the IP address of server 1. Port 22 is open. And now I want to drop connections from any IP address to port 22. So block service TCP 22. Blocking TCP port 22. Now back on server 2, I scan one more time the port 22 and I notice that port 22 is filtered. Yeah, because my script blocks connections to port 22 TCP. Okay, my SSH connection from my Windows recording box already dropped, but that's fine. In this lecture, I'm going to show you how to create a custom firewall for a web hosting server. On our server, run the following services. We have a web server like Nginx or Apache, a MySQL database server, postfix or an email server, a POP-IMAP server, a FTP server like ProFTP, a DNS server like Bind, and the OpenSSH server for management SSH connections. Our firewall has the following requirements. We want to allow incoming connections to all running services from any IP address. Management SSH connections are allowed only from 5 management IP addresses. Then no more than 50 concurrent connections from the same IP address are allowed to the Nginx web server, and all traffic from some hosts inside the same LAN with our server is allowed. We identify those hosts by MAC address. Let's see how it's done. There are some things we must do even if they are not specified. For example, I must flush the firewall. Flush the filter table from input and from output. It's a good idea to comment lines because when we'll return to this script, it will be easier to know what we have done. Or if somebody else reads our script, he will understand easier. IP tables minus F. It doesn't matter what happens with the forward chain because we are not using the forward chain. Our host is not a router. We must permit loopback interface traffic on input and on output. So, permit loopback interface traffic. IP tables minus A input minus I lowercase I incoming interface LO minus J accept. IP tables minus A output minus O LO minus J accept. Okay. Then the first requirement, incoming connections to all running services are allowed. Because there are many services, it's easier to create a variable and then iterate through that variable, allowing port by port. I create a variable permit TCP, and this variable contains a list of allowed ports, allowed TCP ports. For SSH, I have a special requirement. I don't write the 22 port here. The first ports are 20 and 21 for FTP, 25 for SMTP. SMTP also uses 465 SMTPS, SMTP over SSL. Then we have 80 and 443 for HTTPS, 110 and 143, 110 is POP, 143 is IMAP, 993 is for IMAP over SSL. Okay, what other services we have? Nginx, web server, this means ATN 443, database server. Usually the database server uses local connections. We don't allow incoming connections from the internet because the client, the database client, which is PHP or Python or another scripting language, runs on the same computer, on the same host. It's not necessary to have a special line for my database server. Of course, if it must allow incoming connections from the outside, we must specify some IP tables rules. Postfix email server. I wrote 25 and 465, DAFCOT POP IMAP X110, 143 and 993. Okay, DNS server uses UDP. We'll have another rule for that. And for OpenSSH server, I'll have another rule. Anyway, it's very easy to add some ports or to remove some ports from this list. This is the advantage of automation using shell scripts. Now, using a for loop, I will iterate through this variable and I will permit port by port. For port in $permit TCP, do and done. Between do and done, I'll have a rule that allows incoming traffic to my TCP port. IP tables minus a input minus ptcp minus d port $port, because my variable port will have a value from my list, value after value. First, my port variable is 20, then is 21, then 25, and so on. Minus j, accept. As I said, it's a good idea to comment the lines. So here, allowed TCP ports. I must also permit DNS traffic. This means IP tables minus a input minus p UDP. DNS uses UDP minus d port 53 minus j accept. And here I comment the line allow DNS traffic. Then the second requirement is to allow SSH connections from 5 management IPs. I'll have another variable, permit SSH, and now some IPs. First, my Windows recording IP, because otherwise my SSH connection will drop. Let's see what IP I have. I have 192.168.0.145. Okay, and then I'll write some random IP addresses. I don't have specific IP addresses at this time. Okay, that's enough. It doesn't matter how many IP addresses I have, because I'll iterate through this list and I'll permit IP after IP. For IP in $permit SSH, do, done. And here IP tables minus a input minus ptcp minus d port 22 minus s, the packet is coming from that IP address, $IP, the value of my variable that is created and that iterates through that list, minus j accept. I also comment this line, IP addresses to connect using SSH. What other tasks we have? No more than 50 concurrent connections from the same IP address are allowed to the Nginx web server. So permit no more than 50 concurrent connections from the same IP address to our web server. For this task, we'll use the -m con limit match. If we don't remember the options, we could open another terminal and there we write IP tables -m con limit --help and we see the options of this match. I'll use --con limit above 50 with drop. So I'll drop if there are more than 50 concurrent connections from the same IP address. Back on my terminal, IP tables minus A input minus P TCP minus D port. Okay, I have to drop if there are more than 50 concurrent connections from the same IP address for two ports, for port 80 and 443, HTTP and HTTPS. I can write two IP tables rules, or I can use the -M multi-port match with -D ports, and now 80,443. This line matches PECX2 port 80 or port 443. -M con limit, let's see one more time, con limit above. Con limit above 50 -J drop. That's all. Now the fourth task. All traffic from some hosts inside the same LAN is allowed. For this task, I'll use the -M MAC match. First, I write a comment. So permit all traffic from the following MAC addresses. For this task, I create another variable with those MAC addresses and I will iterate through that variable. Allowed MAC. And now I need some MAC addresses. I just take some random MAC addresses at this moment. So I'll take my interface MAC address with copy paste, and I paste it some more times. And I'll modify the last two characters just to have different MAC addresses. For MAC in $allowed MAC do and done. And here my IP tables rule that allows incoming traffic from those MAC addresses. IP tables -A input -M MAC -MAC source, and now $MAC -J accept. This IP tables rule will accept traffic that has the source MAC address that is specified here. Perfect. Till now I have rules that only accept traffic on the input chain. What should we do with traffic that is generated by our server, with the output traffic? For example, I could use the connection tracking feature of the NetFilter firewall and I allow new packets on the output chain. IP tables -A output -M state -state, and now on the output chain I allow new packets. This is the first packet of the connection. Established packets, these are the second, the third, and so on. Established and related -J accept. If I use connection tracking, it's a good idea to drop invalid packets on input and on output chain. So here at the beginning of my script, I write IP tables -A input -M state -state invalid -J drop, and IP tables -A output -M state -state invalid -J drop. I'll use the drop policy on input and on output chain, and that means that these invalid packets will be anyway dropped, but I prefer to drop them faster at the beginning of the firewall and not after all those rules have been checked. And I think I solved all the tasks. IP tables. It was a spelling error here. What should we do? We must set the default policy to drop. Set default policy drop. IP tables -P input drop. IP tables -P output drop. Any packet that hasn't been accepted by an IP tables rule will be dropped. I save the script, make it executable, and run it. Okay, I list the filter table from input and output chain, and I can see I have 28 accepted packets. These are packets generated by my server. Yeah, they are new, related or established. I didn't specify what happens with ICMP traffic. If there is no special reason, it's a good idea to allow ICMP packets. So I open the script one more time. And I want to allow ICMP packets on input and on output chain. I comment what the following lines do. Allow ICMP traffic. IP tables minus P ICMP minus J accept, and IP tables minus A output minus P ICMP minus J accept. If I want this firewall to run automatically at boot time, I must use IP tables save and IP tables persistent, because here it's Ubuntu server. Okay, this is the output. I redirect the output to etc IP tables rules v4. Now, when the server starts, it will automatically load IP tables rules from this file. It's very interesting that anyone can use this script. A user doesn't have to know much about IP tables, or about targets, matches and so on. If we want, for example, to allow some other ports, I just write them here and they are allowed. If I don't want to allow port 25, I just remove the port 25 from my list. I save the script and run it. And the script updates the firewall. If I list the firewall, we can see there is no more port 25, and my new ports like 1111 and so on are there. Now that you had some chances to play with shell scripts, I want to give you an assignment. I want you to create a shell script that requests an IP address and then asks if the traffic from that IP address should be accepted or dropped. Of course, instead of an IP address, you could write a network address. When running the script, after entering the IP or network address and drop or accept string, it should add some IP tables rules that drop or accept traffic from that IP or network address. Now, I want to give you a hint. You can use the read shell command in order to read a variable, and then using an if testing condition, you check if the traffic should be dropped or accepted. Based on the user answer, the appropriate IP tables rules should be inserted into the filter table and input chain. In the next video, I'll show you how would I do it in case you get stuck. Good luck and see you in the next lecture. This lecture is the answer to the assignment lecture right before this one. This is just a recording of me thinking loud and walking through the assignment. Maybe you took another approach and run other commands, but that's okay as long as you get the end result. So I create a script, filter traffic.sh. This script will be run by bash, and now echo -n, enter the IP or network address. Okay, read IP. This is my variable. And now another message that I display, enter, drop or accept. So the user should enter drop or accept. And read another variable I create, let's say answer. Okay, here I have a single quote. You can have single or double quotes. Okay, and now if I want to test the content of the answer variable, so if $answer equals to drop, so here in bash scripting we have a single equal sign. We don't have equal equal, so we don't have something like this. This is not okay. This is the testing condition for a string. Drop, then echo traffic from $IP has been dropped. First, I want to test my if testing conditions, and after that I'll add the IP tables rules. So I only write echo and that message. Elif $answer equals to accept. So the user wrote accept, then echo traffic from $IP has been accepted. Okay, else echo invalid option, enter drop or accept, and fee. The fee closes the if. Okay, here it's better if I put a -n. -n means that it writes or it displays the message on the same line. I save the script. I'll add the execute permission. So 700 filter traffic. So enter the IP address or network address. 6666. Enter drop or accept. Drop. Traffic from 666 has been dropped. Okay, we also need a new line there, but that's no problem. I'll add a new line. One more time. Okay. Accept. Accepted. Okay. And one more time. I want to write neither drop nor accept. So, okay, something like this. Invalid option. Enter drop or accept. Okay, perfect. So we need some new lines. So here we don't need -n. Okay, and here we need a colon. Okay, that's better. And now the IP tables rules. So here I'll drop the traffic. That means IP tables -i. I want this rule to be the first rule because maybe there are many rules. -s $IP. So the traffic is coming from that IP -j drop. And if the user answered accept, here I'll have the same line, so I can copy and paste it there. Okay, and paste. And instead of drop, I have here accept. That's all. I save the script and run it one more time. So filter traffic. Enter IP or network address. Let's say 3333. This is just an example. Drop. Has been dropped. IP tables -VNL. So the line is there. One more time. Let's try ping 8888. Ping works. And now filter traffic 8888 drop. Okay, the traffic has been dropped. Ping doesn't work. It seems everything is just perfect. Okay, everything works, and that's my assignment.